Hello everyone, this is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, LTE-A HetNet, Small Cells, What You Absolutely Need to Know, presented by Azimuth. Our presenters today are Vivek Vadakupatu, Vice President of Product Management and Marketing at Azimuth, and Dr. Charles Wright, Chief Scientist and Director of Systems Engineering at Azimuth. And with that, I'm going to hand the presentation over to Vivek.
Hello, good afternoon. My name is Vivek. Thank you for taking the time to join us here. So a very quick introduction to Azimuth. Some of you might be familiar with us. We were founded in 2002. And if you look at our roots, we really started in Wi-Fi early on. And from Wi-Fi, we moved into cellular. We have a lot of firsts to our credit. The first Wi-Fi test solution, the first MIMO channel emulator, and one of the most widely used field playback solutions as well. And then over the last couple of years, I would tell even within cellular, our focus has been, initially we started with conformance, and really our focus has moved to performance testing. And with performance testing, things such as the field lab that I mentioned was a very big part of it. And in addition to that, we've also done a lot of work with operators in terms of performance test plans. And basically, a performance test plan is all about running a test in a lab and getting results that are as close to what you would see in the field as possible. That's really been our mission. It's been all about how can I recreate the radio environment as closely to the field in the lab as possible, so that when you run a test in the lab, you have the most amount of confidence that the results you see are indicative of what you would see in the field. And most recently, actually just last week, we launched the industry's first HetNet environment emulator. I know today's webinar will talk about HetNet and HetNet interference mitigation algorithms. So I'll take maybe 10 minutes towards the end of the presentation to talk about this new capability that we launched. But essentially, if you look at Azimuth, we started in Wi-Fi, moved into cellular, and the reason I'm mentioning that is this whole move from Wi-Fi to cellular and back to this whole convergence of Wi-Fi to cellular puts us in a very unique position when it comes to HetNet and emerging technologies such as LTE. So with that introduction to Azimuth behind us, let's look at HetNet before we get into the technical details. When we went from 3G to LTE, that was viewed as a pretty big evolution. We went from SISO to MIMO. We went from WCDMA to OFDM. But this whole move from LTE to LTE Advanced is a huge disruption. Now, if you look at what is driving this disruption, to me, it all comes down to one single thing. There is a request, or there is a strong demand for ubiquitous high-speed coverage. People want high-speed coverage everywhere, and whether it's for streaming data or for emerging applications, there's this growing need for data. Now, I'm not even talking about other applications such as M2M, which are not data intensive but are humongous in terms of numbers nevertheless. If you look at how LTE Advanced delivers on this requirement, the way LTE Advanced does this is a totally different approach. What LTE Advanced does, there's a couple of different mechanisms. You use HetNet to improve your capacity. You use small cells to improve your coverage. So you want to make sure that there are no dead zones. So use small cells, and mechanisms such as carrier aggregation and comp to improve your overall data rate and your reliability. But essentially, what you need to take away from this slide is the fact that going from LTE to LTE Advanced is a huge disruption, not just disruption at a physical layer. It is a fundamental paradigm shift in terms of how the network is deployed. So with that, I'll hand it over to Charles, who will talk about HetNet and some of the HetNet interference mitigation algorithms.
Hi, thanks, Vivek. Hi, this is Charles Wright. It's nice to be able to give you this presentation today. So I guess the big question is, what is HetNet? Now, in LTE, what it really means is we have a mix of different cell sizes that are using the same radio access technology, that of LTE. And it causes a lot of interference, and because these mix of cells are all in, they're not laid out regularly like your classic macro cells have been. You want to be able to put out a deployment of small cells in a coverage area to supply some capacity offload or to handle a hotspot of capacity needs. And if you were to stick with your classic macro cell hexagonal cell layout, you just couldn't do that. So this changes a lot of things about the way you do your deployments. For one thing, since bandwidth is king, we end up with, instead of dividing our cells into lots of little skinny chunks of bandwidth like we did back in the old days of AMPS and GSM, we end up taking the entire band for one downlink carrier. And so we inherently have to operate with a frequency reuse of 1. Because these cells end up being inside, the small cells end up being inside the macro cells, it changes the equation for radio resource management. The UE has to have a new decision algorithm for deciding when to do a handover. So those are kind of the main things that make a HetNet. And then finally here, I just want to point out that in terms of terminology, in the past there have been some reference to HetNets being like an older and a newer radio access technology. In those situations, typically there's no interference from that. And so the term HetNet is being used for a completely different reason nowadays. So here we have the main shifts in the network environment. We've gone from a single link, meaning that we have the handset is connected to one base station, to the possibility of connecting to multiple component carriers on the same base station, as well as the possibility of connecting to component carriers in geographically different locations. We want to be able to do this sort of in an unplanned way. The planned way was very expensive, involved lots of driving and determining what the layout should be and where precisely to put the macro cell. What we'd like to do is reduce the cost of all that by being, and enable simply putting down a small cell wherever we might like, because that's where we need to fill a hole in coverage or we need to provide some additional capacity. And because we have our single frequency network here, we end up with a lot of interference. Now, interference was always a big deal even in the older days of higher frequency reuse of, say, frequency reuse 7, where you had you had 7 different frequencies around your hexagonal layout. But now, since there's only one frequency and everything is so much closer together, the interference is not so easily mitigated. So how do we do that these days? Well, with the emerging mechanisms in LTE, we've got this thing called ICIC, which is fun to say, but it just means inter-cell interference cancellation or control. And there have been a range of those efforts that went through the 3GPP. There's comp, where we try to get better cell edge performance by having coordinated transmission among geographically separated base stations. We're not going to talk about that so much today. And all of this is to support this emerging class of devices where there are many, many low bandwidth or high bandwidth, and anyway, I guess you could just say that this is what ends up giving us our disruptive change in the network environment. So that's all I wanted to say on that slide. Okay. Okay, so let's give a quick overview of interference mitigation. So this will we'll focus here on the interference mitigation part, especially at the physical layer, but it's important to realize there are functionalities required within radio access network and in the device. So this all started with release 8 with ICIC, intercell interference control. And we'll have more discussion about that. It moved on to the so-called enhanced ICIC for release 10. This introduced new concepts known as the almost blank subframe and cell range extension. I apologize for not expanding those acronyms out, but you'll see them expanded on later slides. And then there was so much work to do in eICIC that they had to basically cut it off so that they could meet their release 10 deadlines. And so additional work got rolled into release 11 with a further enhanced non-carrier aggregation-based ICIC study item. So, and then this kind of spawned a bunch of other work within 3GPP. There was a small cell study item. It asked, you know, what do we do when we allow carrier aggregation to be thrown into the mix? And then something called NAICS that they pronounce NICS, stands for Network Assisted Interference Cancellation and Suppression, which is a release 12 item. I believe they just finished with the performance specifications for NAICS in this August. There's dual connectivity, another item where we have the possibility of different component carriers or component carriers being located at geographically different places, and introduces a whole bunch of other issues, but makes it possible to do interesting things with coverage enhancements. And then I put ... because I could go on for several more, but they're probably not as important. So now let's look at, on the device side, how is this all being handled? Well, advanced interference cancellation receivers is the answer. Initially, in release 11, they developed the performance specifications and the standard receiver model for the so-called interference rejection cancellation receiver, which does its work by not simply assuming that everything that's not signal is white noise. There's a, I believe it's called minimum mean squared error interference rejection canceling receiver. And then one better is the successive interference cancellation receiver. Now, these successive interference cancellation has been around for a long time in other areas, and I was quite surprised to see it in handsets. But according to a friend of mine, it's only recently been possible that the processing power and the ability to do this without burning up your battery so quickly has actually been made possible. So successive interference cancellation in a handset is now being assumed for these advanced interference mitigation techniques. So let's see next. Okay, so let's talk a bit about ICIC. This is the first interference mitigation that was defined for LTE. So this was developed for regular macro deployments. The user devices provide interference measurement reports, and the network decides how to allocate power in various parts of the LTE spectrum. So the basically, as I said, we have the handsets making these measurements, the eNode Bs communicating across an X2 interface to share information about where in their downlink spectrum the interference is, and then they can allocate power to different parts of the spectrum to give their cell edge users sort of preferential signal-to-noise or signal interference ratio. So as you see here, let's see, am I getting the mouse? Okay, right. So here we've got a guy connected to cell A, and he's in the edge where the eNode B will allocate more power, and he's getting scheduled resources in the higher power area of the spectrum. Now, likewise, the same thing can happen to the user connected to cell B here, and then he gets allocated in part of the spectrum where he has higher power. And then the cell, the users in the more the middle of the cell end up, since they don't require as much power, the allocation is lower where they get scheduled. So there's lots of different ways you can handle this, and it's pretty much totally up to the base station vendor to develop their own scheduling algorithms to best take advantage of this. So let's go on to enhanced ICIC. This was added in release 10, and basically, as I said before, has introduced two main concepts. The concept of the almost blank subframe, where instead of simply changing the power level and frequency, we are going to do it in time as well. So I should have mentioned for regular ICIC, these frequency allocations, these frequency power allocations are on a sort of a long-term basis, and they apply to, they're not time-based. It's basically once you set up what you want your power to be in a certain range of resource blocks, it stays that way over the entire frame and over a bunch of frames until the scheduling algorithm decides to change it. So you could say it's not really time-based, it's totally frequency-based. So for eICIC, we simply decide to not transmit during some of the subframes within our frame, and then we use this other mechanism to achieve what we call cell range expansion. So between the two of those, you can manipulate what the handset's link budget is at various times and in various geographic locations relative to the connected cell and the interfering cell. So with cell range expansion, what we're doing is we change the handover threshold so that a device will stay connected to the small cell instead of deciding to connect to the macro cell. Current rules before cell range expansion would be that whenever one cell has a larger power than another, then the handset would hand over to that stronger cell. Well, if you do that with small cells, then your small cell coverage areas are actually quite small, and simply because of the power ratios between the macro and the small cell, we're talking a difference, you know, in the 15 to 20 dB range. So somehow we need to figure out a way to keep those handsets connected to the small cell, otherwise you're not getting any benefit from it. So what they introduced was a cell selection bias. Now that gets communicated over, I believe it's the system information blocks that are transmitted, you know, system-wide messages in a particular downlink, so that the handset knows that, you know, it's going to basically wait until the other, until its connected cell is, say, you know, maybe 5 dB and even up to 9 dB lower than an adjacent cell, and only then will it decide to hand over to that other cell. So there's a significant difference in power at which you decide to hand over. Make sure that I've said everything I wanted to say. Okay. So continuing, let's talk about the ABS. Let's look at this figure here. We see that we have these various ellipses. The yellow ellipse at the edge between the yellow and the blue, we have equal power between the small cell and the macro cell. And at the edge between the blue and the gray, that is our additional coverage due to the cell biasing, the cell handover bias. Now, the handset needs to stay connected to the small cell. Even if it's in this blue range, it wants to hear the small cell so it can get its system messages and stay synchronized. There's the broadcast channel and there's the various synchronization signals. But it's doing that even though there's a negative, the power from the small cell is lower than that of the macro cell. And then those would be in, if you look at the blue subframes down below here, where I'm showing the mouse, at those subframes we have, you know, both cells transmitting at their full powers. And then in the green areas, the macro cell mutes some portion of that subframe, and hence the term, that's why it's almost blank, because it doesn't do everything, and allows the small cell to schedule handsets which are in that blue region to receive their downlink data. Now, it happens that the control channel and the broadcast channel are pretty robust, so you can receive those with your interference canceling receiver fairly well, even though there's a lot of interference. They're more robustly coded and they don't use a high order modulation. For instance, the control channel is transmit diversity encoded and it only uses QPSK. On the other hand, when it comes time for an almost blank subframe, that's kind of a quiet time where you can get a burst of high rate data, high modulation scheme, perhaps with, two-layer MIMO modulations and codings that require a higher SNR in order to receive successfully. So that's the whole point. It's not simply that we are shutting off these frames, these subframes, and allowing someone else to transmit, because there's always going to be interference from somewhere else. So it's just a matter of reducing the interference enough to do the job that you're trying to do. Now, another interesting thing you can do, you can realize that these ABSs take away from the macro cell's time on air, and it does. But if you were to deploy small cells throughout the macro cell coverage area, then those other small cells could take advantage of the ABSs within their own geographic region and successfully supply a higher data rate to users local to those other small cells. So as I sort of alluded to earlier, ABSs are not perfect. There is still interference from the control channel and the cell reference signal. The control channel will be transmitted to provide uplink grants to the handsets on the return link, and the cell reference signals are expected to be present in all subframes because that's basically a legacy fact. We need to handsets from release 8 are always expecting the cell reference signals to be present, and if they go away, then it gives them some heartburn. So we can't simply shut off the cell reference signal. There is another type of ABS, which I'll get to on a later slide, where the cell reference signals are not transmitted, but we'll get to that. Let's see. So yes, let's look at how ABSs work in more detail. So the ABS pattern, as I said, indicates when the macro cell is going to be blanking its transmission. And this information is exchanged over the X2 interface between the macro and small cells. It's the backhaul. Special interface, I believe it was introduced relatively later in the game to allow eNode Bs to communicate. How often the macro blanks is determined by what we would call an ABS ratio. The higher the ratio, the more subframes that the macro will blank. And below there you see some examples of different patterns. It's not completely arbitrary how you select your ABSs. You have to be able to still support your uplink hybrid ARQ. Hybrid ARQ generally requires access to the channel every 8 subframes, and so we can't have an ABS every 10 subframes, because the HARC processes would not be able to communicate their acknowledgments. In this case, it would be the eNode B communicating an acknowledgement about packets received on the uplink. So that's in our first row we have, relatively low utilization, 12.5%, and then if we double up those subframes, we get 25% utilization for the small cell. The third row shows another case of 25% where they're more often. This might, there we go. That might be necessitated by, you know, these guaranteed bit rate services needing something that's periodic on that scale. And then finally, in the last row, we have a different sort of ABS, and that's my final bullet here. The so-called regular ABS, the data channel is simply muted. For the acronym AWARE, that would be the physical downlink shared channel, the PDSCH. And if you just shut off the PDSCH, that leaves the reference signals and the control channel or the control area of the subframe still active, so with power being transmitted. So that would be a regular ABS. And then there's a feature in LTE that allows a special kind of subframe to be transmitted. It's meant for something else. It's meant for a multicast broadcast purposes, but the main point is if there is no one scheduled to receive multicast broadcast data, then we can change the use of this subframe, the MBSFN subframe, to be simply a gap in the transmission. So in the MBSFN subframe, we're only transmitting the control symbols, and the rest of the subframe is blank. Now, it does have some restrictions because the MBSFN subframe can only occur in subframes 1, 2, 3, 6, 7, and 8 instead of any subframe like the regular ABS. So that is the ABS as a mechanism. Now, the combination of the ABS and the cell range extension give you a lot of different ways to trade off your system parameters to achieve best capacity. The cell range expansion region allows more users to call a cell home, but the more users that small cell has, the more ABS that are going to be required. But this takes away from the macro capacity. There's a trade-off that has to be made here. We want a large cell range extension region to capture more devices, but the larger we make that, the more potential and the more users that are in that small cell coverage area, the more likely we're going to need more ABSs to support those users. And of course, if you have small cells dispersed throughout the macro area, this complicates the equation further and gives the guys at the base station companies a lot of interesting work in scheduling algorithms. So clearly, with this trade-off, there's testing of system-level performance is a critical thing. So, oh yeah, I guess I should say part of the interesting thing about this is this trade-off is not a static trade-off. It's possible for this to be done dynamically in response to the needs of users as they come within the range of small cells. So, hence, you know, you have your X2 interface and various interference reports from users and communicating with the small cells, this information getting into the network and driving these optimization algorithms to ultimately decide the scheduling and the selection of the ABSs and the scheduling of the users onto particular parts of the downlink. And so for as I said, the further enhanced ICIC, there this was extension of work for release 10, targeted for release 11. There were some unanswered questions that they had, and they needed to spend more time on it, but if they had spent the time, then they would have delayed release 10, which would have been a bad thing. So things like, would they need additional signaling requirements in place to support various things that they wanted to do, how to address interference from the cell-specific reference signal in the normal almost blank subframe, interference from the control channel not addressed by eICIC. One thing I didn't really mention was that there's a very big assumption here that eNode Bs will all be synchronized with each other, so that in the case of ABSs, that they happen at the right time. Clearly, that's a difference from the past, from some protocols that don't require synchronization of base stations across a large area. But here with ABSs, we're clearly needing synchronization. And you might ask at what time scale that synchronization is required. Well, I would say it's pretty short time. The synchronization is on the order of a couple of microseconds. And since the standard in many ways simply provides a bunch of mechanisms, the ABS and the cell range expansion or the cell handoff bias, selection bias being a mechanism, both being mechanisms, and synchronization is another mechanism. So there were simulations where they evaluated the possibility of simply offsetting the time alignment between cells. Instead of lining them up at the exact beginning of a subframe, they might delay one cell with respect to another by the number of control channel symbols. So that would be, 1, 2, or 3, which would be, on the order of 72 microseconds per symbol. So they would delay, and the benefit there would be that in some cases the only thing interfering with the control channel would not be another control channel, but the downlink shared channel. At any rate, it's kind of up to the operators and base station vendors to decide how best to use these various features. There was a lot of discussion about sort of reduced power ABSs. So it's not only is it not completely blank, but they're transmitting simply at a lower power level. Again, the magic here is that we don't need, we're transmitting in a regime where there's always interference. We can never simply get, white noise as our degradation. And so there was discussion about advanced interference cancellation receivers further in this FeICIC. And as I mentioned before, it spawned many new study and work items. There was a small cell study item that discussed how to bring carrier aggregation into the picture. There is the NAICS. I can just say a little bit about that. Basically, if you know what your neighbor's cell IDs are, then it makes it a lot easier to predict, well, you can totally predict what the cell reference signal values will be, and you can cancel them out a lot easier. that's just one example. Well, there was discussion of that in FeICIC, and I think somebody said, well, what if we knew all these other things as well? And like transmission modes and the power ratios between the reference signal and the downlink share channel. And the more you know about your neighbor, the more the less power you have to consume in figuring out what the interferer is transmitting so that you can cancel them out. Obviously, there's a trade-off, because if you knew everything about what the neighboring cell was transmitting, that would basically double your bandwidth needs. So like I say, there is a trade-off in terms of the number of parameters that end up being conveyed by the network in NAICS. Then there's dual connectivity, which is, again, the idea that we don't need to have our component carriers at the same location. There are a lot of new problems introduced by that idea. And then a recent study item, I believe going to be turning into a work item, is cell reference signal mitigation. And that's, I believe, it doesn't involve knowing ahead of time what the cell ID is. So, and there's others as well that I'm not really familiar enough to talk about. So, and now, thanks for listening, and I'll turn you back over to Vivek.
Thanks, Charles. So with that, we spoke about the different HetNet interference mitigation algorithms. So let's talk about how you test HetNet. In many ways, if you just listen to what Charles told, it's very fascinating, right? It's almost like what happened on the handset side. You went from a very simple feature phone where all that you could do was a phone call or maybe a text message after punching 1,000 buttons. You've gone from that to smartphones, which does much more than just phone calls. Smartphones are such a big part of everyone's lives. It's something similar that has happened on the technology front. We went from these very simple networks, or the early days of LTE, where you set up a single connection, you were happy with that, to a point where right now you have multiple connections, very complex HetNet environment. So what all of this means is the way you test HetNet has to be different from how you test LTE. Just like technology evolved from 3G to LTE and LTE to LTE Advanced, the testing that you use also has to evolve. Very simple analogy is you can't take a F1 car, put it on a go-kart track and test it out. The testing has to keep up with what you're trying to test. Okay, so let's look at how you test these different HetNet interference algorithms. Now, you might start by telling, I'm just going to go to the field and test it. Okay, testing it in the field is required, but it's not a very viable option, or testing it just in the field is not a very viable option. Any of you who've done field testing know the challenges associated with field testing. It's not repeatable, it's very cost expensive, and it's not under your control. The field is what it is. Now, you already take such logistical challenges that you have, and if you have to test a complex technology like HetNet, trying to do all your testing in the field is just not scalable. You'll spend the rest of your life just driving around hoping to test these different algorithms. So then you ask, if I can't test it in the field, how do I test it in the lab? For you to test HetNet in the lab, there are two things that need to happen. The first thing is you need to create the HetNet environment. The environment I'm showing you here is no different from what Charles covered. As Charles told, when we went from LTE to LTE Advanced, the network architecture has changed. You no longer have these beautifully laid out hexagonal slides. You have more of a very, very cluttered network, if you will. So what you see here is I have my serving cell and then a couple of other cells that I'm going to jump to at some point of time. but then I also have these interferer cells. So essentially, the first step is for me to create a HetNet environment. Once I create the HetNet environment, the fun does not stop. Creating the HetNet environment is just the first piece. The second piece is once you create the HetNet environment, if I want to simulate mobility or I want to simulate the instance where I'm a user, I'm at home, and from home I go out to a Starbucks, and from a Starbucks I go to a shopping mall. How do I recreate this entire environment? So you have to create the HetNet environment, and once you create the HetNet environment, you need to control this HetNet environment so that you are able to test these different scenarios that are relevant for these algorithms. So how would I do this testing in the lab? I've told you what we need to do conceptually, but what does it translate to in terms of the actual details? One way for you to do this testing is by using a test bed like this. So I have two serving cells, I have enough interfering cells, and now what I do is I want to make sure that now that I've created the RF environment, I want to control the RF environment. So these blue bubbles that you see essentially show the fact that not only do you stop at creating the HetNet environment, you have to move on and control the HetNet environment. Beautiful. So I've shown you how to do this, but as you can see, this is not a very practical setup for a variety of reasons. One is it's very complex to set up and use, not to mention that it's very expensive, prohibitively expensive. And then the last thing is, these are all live infrastructure. I'm still using live infrastructure to be my interferers. Anyone who has used live infrastructure knows the challenges with it. Simple example, if I tell my small cell is in the presence of a macro cell and I want to change the cell ID of the macro cell from 100 to 101, I can't change that on my own. I have to open a ticket, my infrastructure vendor comes and changes it. So there's a lot of challenges associated with using live infrastructure, especially in the context of being your interferer. Now, people have taken this and created different variants from it. I won't go into each of these in detail, but the way to look at this is when you go from option 1 to option 3, option 1 is probably the most complex, but most indicative or reflective of the actual environment you see in the field. And option 3 is where you tell, you know what, option 1 is too complex. I can't deal with option 1, so I'm just going to take it and dilute it. You dilute it by cutting down the number of interferers, or even taking it a step further and telling, why should I use a macro or an actual cell to be my interferer? I'm just going to take a signal generator and hook it up. Now, the thing to keep in mind here is, while this might look simpler, this is not accurate. Like, you might as well not run this test case at all, because in the real world, for mechanisms like ABS, almost blank subframes that Charles mentioned, for these kind of mechanisms to work, the interferer that you generate has to be time synchronized with the serving cell. So essentially, like, what it really forces you to do is, if you want to test HetNet in the lab, you have to test it with a setup that looks like option 1 or option 2. Okay, so all of you are thinking, so you told me I can't test HetNet in the lab. You told I have to test HetNet in the, you told you can't test HetNet in the field. So you told you have to test HetNet in the lab. And then you show me a Frankenstein of setup that I have to use to do my testing. So what real option do I have? What can I do? What other choices do I have? That is something that kept all of us up, and that's really what led us to launch this game-changing capability, first time in the industry, called virtual network environment. So what we told was, hey, our goal at the end of the day is to help you test HetNet. To test HetNet, I have to help you create a HetNet environment and control this HetNet environment. So what we did was everything that you require to test HetNet, to essentially create a HetNet environment, we took all of that and integrated it into our RNX platform. The RNX is an environment emulation platform for LTE-A HetNet and other emerging technologies. So essentially, what VNE, virtual network environment, does is it creates all these interferer cells that you require, and it does everything elegantly inside the platform, so that you go from this ugly contraption, this real Frankenstein that you have to use to create the HetNet environment, to a very, very elegant, controllable setup. That's really what VNE does. Look at this. This is just beautiful. I mean, you take this entire HetNet environment that you require, and you put it inside the platform so that it's simpler from a footprint standpoint, and more importantly, it's more manageable. Just one more slide on this capability in detail. So essentially what this provides is VNE gives you the ability to create an LTE downlink interferer. Now, as you notice here, it is a fully controllable cell. What I mean by a fully controllable cell is it's up to you as a user to decide whether you want it to be a small cell or a macro cell. Now, I can make it a femto cell, pico cell. It's entirely up to you. You can configure all the cell parameters. How many antennas does my cell have? What transmission mode am I using? What loading am I seeing? How many people do I have on my cell that is causing the loading of the cell? So you as a user have total control over how you're configuring these cells. Now, going back to what I mentioned a couple of slides back, live infrastructure, making changes to live infrastructure is not very easy to do. Many times you will find that you may not be able to change things directly. One of the advantages of VNE is the fact that if I want to just go change the cell ID or tell, hey, how does my small cell perform when I have a macro cell near me and the macro cell uses ABS pattern 1 and I have another macro cell that does not use ABS or uses ABS pattern 2. For me to go test these different permutations and combinations, all the changes can be done at the click of a button. So you have total control over these interferer cells and how these interferer cells are configured. Now, obviously, when we talk about an environment, as all of you know, the environment has two pieces. You have these interferers and then the actual conditions or the channel conditions through which they propagate. With VNE, not only do you have the ability to configure the actual channels, but you also have the ability to control the radio conditions the cells propagate through. This is very important because what it means is for me to create this environment where I have the device moving from here to here, any kind of mobility, you have the ability to condition the channel as you need it to be. The last thing when it comes to VNE is these interferers are synchronized. What I mean by synchronized is every interferer that VNE generates is time synchronized down to a subframe level to the serving cell. And the reason this becomes important is, as you know, things like ABS, the interference mitigation algorithm, ABS entirely relies on time level synchronization down to the subframe for it to be able to service devices sitting in the CRE region. So if I come and tell you, don't worry about using live infrastructure, use VNE, I need to make sure that whatever interferer I generate is fully time synchronized with the serving cell. Now the synchronization we do with this is all done over the air. There is no external sync. I mean, have any of you seen like a macro infrastructure or a small cell with an output port called sync or trigger? There is no such thing. So the only way for you to synchronize with an actual serving cell is over the air. So we've done something very, very smart. What we've done is we built a synchronization receiver inside the RNX so that what we do is, first thing we do is we look at who the serving cell is, we time synchronize with the serving cell down to a subframe level, and then we start generating these different interferer cells that you have configured. So now you are creating an accurate HetNet environment, and once you've created this accurate HetNet environment, now you are able to control it and run your test cases. The last thing I wanted to cover was how are people in the industry using VNE? We already have some operators and infrastructure vendors who are using VNE, and we are beginning to see significant reductions in the time it takes for us to recreate issues, and obviously any time reduction accelerates time to market and also translates to cost savings. If you look at what people can use VNE for, now these are just some typical uses. Obviously there is a lot more you can use VNE for. People use it for testing different HetNet interference mitigation algorithms such as ICIC or any flavor of ICIC, NAICS, or advanced interference cancellation receivers that Charles mentioned. So these are the test areas. Now, specifically, what do people use this for? People use this for testing, doing pre-launch testing. I should have actually mentioned it's not just pre-launch testing of small cells, but they use it for pre-launch testing. Pre-launch testing is where you do, if I'm an operator or if I'm an infrastructure vendor, for example, I would tell, hey, this operator requires me to run through these test cases and make sure that when I'm a small cell and I'm in the presence of a macro cell, when the macro cell goes blank, I'm able to serve a device sitting in my CRE region. So that is device qualification. And then interoperability testing. Now, interoperability testing, typically most people look at interoperability testing in the context of device interoperability, but a very important thing to keep in mind here is macro small cell interoperability. One of the things we heard a lot from operators and both small cell and macro vendors is people are very concerned about how a small cell from vendor A would interop with a macro cell from vendor B. So people are using VNE today to test some of these aspects. Second thing is deployment. So you see a lot of announcements where operators decide they're going to roll out 100,000 small cells, 300,000 small cells. How do you know what is the ideal setting, ideal configuration for you to use? How do I know should I mix vendor A, vendor B, or vendor A, vendor C? So doing more and more of this work up front in the lab before you deploy it in the field, which will lead to significant savings. So that is the second use case. And then the last use case is post-launch testing. Now, post-launch testing can be two things. One is regression testing. What that means is if I'm an operator, or let's say I'm a small cell vendor, I get a new build from my chipset guy, you want to make sure that when you went from build A to build B, nothing broke. Because you want to do all this testing in the lab. The worst thing you could do is take a new build, deploy it in the field, and find that the whole network goes down. So people use it for regression testing. And then the last thing people use it for is actually recreating field conditions. Now, we told you how testing HetNet in the field is very tough. So if you have a customer who sees an issue, this actually happened during a beta trials with one of our customers. They had, this is in a stadium, and they had an executive from the company who was at this stadium, and they saw instances where the device kept ping-ponging between a macro cell and a small cell. So naturally, the vendor was under a lot of pressure to figure out what was going on. Traditionally, if you had to go debug it, what you would have to do is go camp at the stadium and figure out what's going on. Instead, what they were able to do is capture a snapshot was what was happening in the field and come to the lab and recreate this environment using VNE. And they were able to recreate the issue within a week and figure out what was going wrong. So that is that is really the power of this technology. You can use it for your pre-launch testing, deployment, or even your post-launch testing. So with that, I know we are up on the hour. So we want to thank all of you for joining us today. We have much of what we covered today in terms of the HetNet interference mitigation algorithms is also available in a white paper on our website, www.azimuthsystems.com. You'll also find a video version of the same topic on YouTube. Please reach out to us if you have any questions through info@azimuthsystems.com or through Twitter. Thanks, Kyle. I know we have a couple of questions. So if you want to move to questions, maybe we could take a couple before we move on.
Yeah, absolutely. We're running low on time, but yeah, we'll jump in and get to a couple of questions. And for any questions we did not get to, our presenters today will receive a copy of those questions for future reference. First one coming in. So you mentioned that eICIC can use standard or custom ABS patterns. Can you give a little more color on custom ABS patterns?
Sure. So actually, I don't think there's a list of standard ABS patterns. There are simply ABS patterns that fulfill certain requirements of the downlink operation. I mentioned that hybrid ARQ requires responses within 8 subframes. So if you had an ABS occurring every 10 subframes, then you would really mess up the HARC algorithms. Also for other, specific, high, thinking of low latency or very specific data rate services that might need to be scheduled at a certain point to achieve their cost goals, then you can't set up a configuration of ABSs that would violate that. The ABS patterns that I showed, I found in the gray LTE book by Cecia Baker and I forget the third author. I think it was Tufik. And so you can find some ABS patterns there. If you want to, the closest thing that comes to a quote unquote standard ABS pattern would be found in the performance specifications in document 36101. But those are for specific radio conformance test cases and don't necessarily represent something that you would use in real life.
Okay, great. And I think we really have time for just one more question, kind of a companion one. So what is the difference or pros and cons of ICIC versus FSS, frequency selective scheduling, and which do you feel is better to use?
Sure. That's, I was trying to answer that online, but verbally is probably better. So my understanding of frequency selective scheduling is that it allows, well, it's basically the base station assigning resources for the handset to transmit based on optimal channel conditions. So if you're in a deep fade on one frequency and not on another, and your channel quality indication measurements can show that, then the base station will put you in a section of the resource grid where there's favorable channel quality. So that would happen on a very short time scale on the order of, within subframes or frames. Now, ICIC is a much longer term thing. You can almost think of it as an agreement between different eNode Bs about which section of the radio spectrum they're going to be transmitting louder in. So, if they're going to be, transmitting higher power for their edge cell users, and that might be, a handful of resource blocks persistent over time until interference went away. So that's really not the same thing as a channel channel effects reason for scheduling selectively over frequency. I hope I understood the frequency selective scheduling part of the question correctly.
Okay, great. Yeah, no, that was a great answer. Thank you for that great webinar. And also I want to thank everyone for attending today's webinar, LTE-A, HetNet, and small cells, what you absolutely need to know, presented by Azimuth. Again, our presenters today were Vivek Vadakupatu, Vice President of Product Management and Marketing at Azimuth, and Dr. Charles Wright, Chief Scientist and Director of Systems Engineering at Azimuth. Thank you, Vivek and Charles.
Thank you. Thanks.